Our next speaker is Noam, who's going to be talking about a cool logic that marries sort of over-approximate and under-approximate reasoning. So, take it away.
Yeah, thank you. My name is Noam Zilberstein, and so I'm going to be talking about outcome separation logic. And this work was joint with Angelina, Saliling, and Alexandra, Silva, and all of us are from Cornell. So the key question in this paper is, can a single algorithm handle both verification and bug finding? And so to begin to answer that question, I first want to say a few words about what incorrectness is. So all this incorrectness stuff is kind of spurred by incorrectness logic, which was introduced by Peter O'Hearn in 2020. Of course, he didn't invent incorrectness, but he did identify these two properties of incorrectness analyses, which are very important in terms of practical implementations of bug finding tools. So the first one is true positives, which basically means if your bug finding tool says that there's some bug in the program, that behavior should be something that is actually realizable by a trace of the program. So we'll see in a minute what that means. The second one isn't so much a soundness concern, but more an efficiency concern. So under approximation basically means that you should be able to find bugs without inspecting the entire program. And that makes analyses more efficient because they can just kind of go down certain paths that look fishy. Okay, so let's look at what do bugs look like. Here, this program has a bug. This is an incorrect program. Why is this program incorrect? Well, malloc is nondeterministic, so malloc may return null. And if malloc returns null, then this memory dereference on the second line is going to segfault. Okay, so let's see what happens if we try to specify this bug using a standard program logic like Hoare logic. In Hoare logic, the post condition applies to all possible end states. So the best we can do is basically use a disjunction to say that there are two states that we could end up in. Either the execution succeeds and x points to 1, or the program crashes because x is null. And the question is, does this actually characterize the bug? And the answer is no, because we don't actually know that the error is reachable. And so to kind of demonstrate this further, let's look pictorially at what this specification looks like. Okay, so in Hoare logic, you kind of get a precondition and a postcondition, and so we can represent this in a picture by showing the blue circle represents the precondition, the green circle represents the postcondition, and what the triple says is that if you start in any state in the blue circle, then all the behaviors of the program end up inside the green circle. And so the program we were looking at has two outcomes due to nondeterminism. One is the OK and one is the bug. And the question we ask is this bug possible? And the answer is not necessarily, right, because we could actually substitute in a different program that also satisfies this specification, but it doesn't have any trace that hits the bug. So we don't know. So in the solution that we use in outcome logic to address this problem is to say, well, why should we just get one circle to draw around all of the possible end states? We should basically get a circle for each reachable outcome. Okay, so we can draw a circle around each of these non-deterministic behaviors, and we say each of these things are reachable outcomes for the program. So what that looks like formally is in outcome logic, we have triples, very similar to Hoare logic, so we have preconditions and postconditions, and the meaning of these triples is that if you take a set of states that satisfies the precondition and you run the program in all of those states, then then the set of states you end up in satisfies the postcondition. So the important distinction here is that the pre and post condition are now satisfied by sets of states rather than individual states, which is going to allow us to talk about the branching structure of the program. And to do that, we have these assertions called outcome assertions. So we have some typical constructs here like conjunctions and disjunctions, and then we have some new stuff. And so the first new thing is this O+ operator, which we call the outcome conjunction. And what this basically says is you can take the set of states and divide them up among the two assertions, phi and psi, so that some of the reachable states are satisfied by phi and some are satisfied by psi. And we'll see in a second an example of what this looks like. And then the second construct I want to point out is just the kind of the basic atomic assertions. So here, if you write P, where P describes some set of program states, what this means is that P describes all of the reachable outcomes, but also that there are I mean, the set of outcomes is non-empty. So we know that this is actually a behavior that can be reached. Okay, so we can now use this to specify a bug in outcome logic. So what we've done here is we basically just replace the disjunction that we saw earlier with the outcome conjunction, and that tells us that these states are reachable. So we now have a guarantee that this error, that there's actually a trace that gets to this error. And then, so this is the true positives property that I mentioned at the beginning. We know this error is not vacuous, but we kind of have a problem because we're not meeting the under approximation guarantee. Because so like, if we wanted some some analysis that would find this bug by only looking at a portion of the program, it's not obvious how we would do that with a specification like this, right? So we're recording this outcome that is not really relevant to the property we want to express. And to fix that in outcome logic, what we basically do is we rearrange the post condition, and we just replace the outcome that we don't care about with top, where top is a vacuous assertion that is satisfied by any set of states, including the empty set. So what this specification says is that the error is definitely reachable, but then there could be other outcomes too. There may not be, but there could be. And so if we go back to the picture, what the new specification is saying is basically there's this transition, there's this behavior of the program that is non-vacuously satisfied by a bug, and then we took all the other possible end states, drew a big circle around them, and just said, we just said true, so there's kind of like no information. Okay, so this is kind of how we can use outcome logic to specify bugs, but the next question is, how can we use this to develop analysis algorithms? And to answer that question, I'm going to kind of use Infer, the Infer tool, which is developed at Meta as a case study. So the classic algorithm of Infer was really a correctness algorithm, and it reported results in terms of Hoare triples, where the precondition would be some start state, and then there would be a big disjunction of end states, which, due to kind of abstract interpretation, it would be possible to merge some of these disjuncts, but if for maximum precision, you would record all of these things. And then more recently, Infer has been adapted to also have an incorrectness or a bug finding mode called Pulse. And what Pulse does is it represents bugs using incorrectness logic, where the post condition is just referring to some reachable outcome. And so the issue with this is that we're now reporting two different types of specifications and two different program logics that are semantically incompatible, so they can't really be used as part of the same tool. Whereas in outcome logic, we can create similar algorithms, but where we give both types of specifications in the same logic. So the correctness specifications, again, enumerate all the reachable outcomes, but now with outcome conjunctions so that we know that they're reachable. And the incorrectness specification drops information about the non-erroneous outcomes. And so there is kind of a common denominator between these so that we can use the same algorithm for both. Okay, so now I want to talk about how do we actually build algorithms that do this, and in particular, compositionality. How do we get compositionality, which is kind of the key to effective program analysis? So program logics already give us some amount of compositionality, sequential composition, so that when we have a program that's composed, or it's a sequence of two smaller program fragments, we can analyze the program by analyzing each fragment on its own. The problem is that these specs that we see here in the premise of the sequential composition rule might be pre-computed, right? So we may not want to actually go back and reanalyze the procedures that they refer to. And then the particular problem is that the pre-computed specifications may not actually match up, right? So the post-condition of the first one might not match the precondition of the second. So the question is, how can we use this rule given pre-computed specifications? So one thing we can do is we can use separation logic, which gives us an additional type of compositionality, which is spatial compositionality via the frame rule. So what the frame rule basically says is if you have some local specification that's only talking about the specific memory footprint that the procedure uses, then you can augment that with information about other parts of the heap. So that's great. And so we've added to outcome logic the ability to use the frame rule and spatial compositionality. And the way that kind of works is that when you have a bunch of outcomes and you want to apply a separating conjunction to them, the separating conjunction just distributes inside of all of those outcomes. So you can just add the frame to each individual outcome. Now, the reachability of these outcomes did present a bunch of soundness issues. Well, not issues. They were solved in the paper. But it was very non-trivial, very subtle. So I'm not going to get into all the technical details, but I'm happy to talk about that offline, or you can check out the paper. Okay, so what does the frame rule allow us to do? Well, there was this work on bi-abduction, which is now about 15 years old, which it provides this procedure for reconciling two separation logic assertions. So if you have some P and some Q, and you want to know how can I sequence these together, bi-abduction will find the missing anti-frame and leftover frame that you can add to these two things to make them to make the first entail the second. And with bi-abduction, we can create a new sequential composition rule where the two pre-computed specifications don't match each other, and we use bi-abduction to find these pieces that we can add to them with the frame rule to make them go together. I mean, bi-abduction isn't guaranteed to work, but in practice, this has been a very successful technique. The thing is, so we can use bi-abduction in outcome logic, but outcome logic has additional forms of compositionality, or additional types of composition, namely branching. So if you have a program that branches into two outcomes, so here C1 and C2 represent two non-deterministic possibilities, two non-deterministic paths that the program could take. Now we have a similar rule where we would want to analyze this type of program compositionally, but what if we only have pre-computed specifications where the preconditions don't match? And to solve that problem, in this paper, we introduced a new entailment procedure, which we call tri-abduction. So tri-abduction is similar to bi-abduction, but there are now three unknowns. So you have a missing frame still, and then two leftover frames that you have to find. And the way that we use this is we can create this branching composition rule with tri-abduction, where we have our two pre-computed specifications. We use tri-abduction to find the precondition that's kind of like the common precondition among them, and then we can add the leftover frames to the two postconditions. So this allows us to analyze branching behavior compositionally. It also solves another problem with bi-abduction algorithms, which is that most bi-abduction algorithms have to analyze the program in two passes, but tri-abduction actually allows you to analyze a program in a single pass, which is quite nice. Okay, so let's see how can we use all these ideas to write algorithms that analyze programs for both correctness and incorrectness. So this is kind of going back to the example I had at the beginning. Here we have the malloc procedure. As you would imagine, malloc is a very commonly used function. So it's going to be used all over the place in your code base for both correctness and incorrectness. And so it makes sense that we would have some maximally specific specification for it that specifies all the reachable outcomes. But from this, we can derive two new specifications by just dropping the respective outcomes. And if you were writing an incorrectness analysis, you may use some heuristic to say, well, if X might be null, that's kind of a suspicious situation. So we could select that specification and use that in a sequential composition with the next command, which we saw before. And here we would see that if X is null and we then execute a memory dereference, the program will crash. And then the true outcome, we can just kind of push it forwards using a vacuous rule because this triple with both pre and post condition of true that specification holds for any program. And then we get the bug specification that we saw at the beginning. So with that, I'm gonna conclude. So we saw how outcome separation logic allows us to witness the reachability of many outcomes. And because of that, we can use it for correctness and incorrectness. I didn't get into this, but the algorithm we have in the paper actually also works for probabilistic programs. So that's pretty nice. And all of it's powered by local reasoning with the frame rule. And so using tri-abduction also, we were able to create compositional algorithms for these programs with branching and reuse specifications. So now I'm happy to take questions.
Can you just say one more sentence about probability? Like, so
Yeah.
does O plus operate over distributions instead of sets?
Yeah, so you can think about you can think instead of O plus being like dividing the set of states, you can think about more generally that there's some sort of like mass of the collection of states. And so you could think about that like a set where you divide it, but it could also be like you're dividing up the probability mass. Yeah.
Thanks for the talk. So to my understanding, and I might have misread the specification here, but for your triples, you're saying for all states in the precondition, each state must satisfy all of the outcomes in my postcondition, modulo whatever, like algebra your outcome. So like say nondeterminism if you're doing sets. How does that work with your claim that you can do under approximation? Because then I'd assume for something like a loop, you still need to prove for all states that every single state can reach whatever outcome you're interested in. So you can't say for only like some unrolling of the loop that they satisfy that outcome.
Yeah, so first of all, under approximation can mean several different things. Like in the incorrectness logic literature, what they mean is, in Hoare logic, we say that the postcondition over-approximates the strongest post, and in incorrectness logic, it under-approximates the strongest post. Here, it's a subtly different understanding of under-approximation, where we're saying we're under-approximating the set of reachable states by kind of ignoring some of them, or by like vacuously satisfying them by true. So you can do similar stuff. Like if you wanted to analyze a loop by doing bounded unrolling, so you just unroll like n times for some fixed n and then stop, you can still do that. So in incorrectness logic, if you want to do that, you kind of need to have the information about why the loop stopped in the postcondition, because the postcondition has to be very precise. Everything in the postcondition must be reachable. So you can kind of do the same procedure with outcome logic. It's just that the information about why the loop is going to stop has to be in the precondition. So it's sort of the same information, it's just where you're specifying it. And actually, the algorithms that they've implemented that at Meta inside of infer that they've implemented for incorrectness, they actually specify those conditions in both the precondition and postcondition. So it's interesting because you can actually interpret those triples as either incorrectness logic or outcome logic. So yeah, I hope that answers your question.
That was a great talk. I learned a lot. So I have a question about your treatment of non-determinism. So, and I think normally I never care about this, but in your logic it seems to matter, which is your non-determinism is binary, meaning it has two choices. And it looks like your choice rule uses those two choices. What if the non-determinism comes from guessing the length of an array or something that is basically not a finite area operation? Like, do you have a rule that can handle that, or what would you do?
Yes, yeah, so we use some programming language that has this binary choice operation, but we're also, I mean, maybe not in the exact formalization from this paper, but in general, we would allow you to kind of add your own atomic actions. And so you could have some atomic action that has like infinitary non-determinism. There are issues with that if you want to do total correctness. So unbounded non-determinism doesn't work well with total correctness. But if you only want partial correctness or incorrectness, then you could do unbounded. And then, I mean, the outcome conjunction, the like O plus, is kind of binary. You could have an infinitary one, but it depends what you're trying to do. Like, if you want the postcondition to be like finitely representable, it may be an issue, but yeah.
No, actually, one last question, Jeff.
Okay. Hey, Noam, great talk. If I remember correctly, with bi-abduction, there's usually more than one sound solution, and so many algorithms decide to approximate because it is a very infeasible problem in many cases. Is that more difficult with tri-abduction?
So we use some of the same tricks where, like in bi-abduction, one assumption they make is if you have if you have x points to something and y points to something, they assume that x and y don't alias each other just to cut down on the space of solutions they need to do. So we kind of use the same heuristics as in bi-abduction because that's what has been shown to work. But yeah, I mean, tri-abduction also has many possible solutions. So we try to come up with like a minimal one if we can, but yeah.